Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at Regenesis and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please try refreshing your browser. If that does not fix the issue, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will look at groundwater and contaminant mass flux and a modern approach to measuring, reporting, and designing with mass flux data. With that, I'd like to introduce our presenters for today. We are pleased to have with us Dr. Paul Erickson, Director of Research and Development at Regenesis. Dr. Erickson oversees the commercialization of new environmental solutions to address complex remediation challenges. In his time with Regenesis, he led the development of a number of remediation products and technologies, including Petrifix and Flux Tracer. He earned a BS degree in chemistry from Florida State University, a master's in chemistry from the University of Minnesota, and a PhD in environmental chemistry from ETH Zurich. He's an author of over 20 peer-reviewed scientific publications, mainly in the area of environmental chemistry. We're also pleased to have with us today Craig Sandifer, Vice President of Remedial Applications Development at Regenesis. Craig has over 20 years of experience in the areas of in situ soil and groundwater remediation, and is a recognized industry expert in the areas of in situ remedial design and applications. In his current role at Regenesis, he's part of a team of geologists located throughout the United States that provide remediation designs and optimize performance for Regenesis clients. Under his direction, the technical services team at Regenesis developed a design verification testing, or DVT, program, a suite of field sampling and testing activities carried out prior to subsurface remedial reagent and placement. DVT has resulted in significant improvements in the identification of contaminant distribution in heterogeneous aquifers. He's also directed and implemented a series of Flux Tracer studies on select sites. All right, so that concludes our introduction. Now I will hand things over to Paul Erickson to get us started.
Thanks, Dane, and thank you everyone for joining us today. I'm excited, along with Craig, to present on this topic that we spent a lot of time lately thinking about and integrating into our approach here at Regenesis to designing and implementing effective field remediation strategies. So just a quick overview of what we'll talk about. So first, I'll give an introduction into mass flux. So we'll take a look at a very fundamental level about what mass flux is, and how it pertains and how it's related to groundwater remediation. And after that, I'll hand things over to Craig, where Craig will talk in more detail about measuring mass flux on for the remedial design at the remedial design level. And after that, he'll get into some discussion on mass flux measurements versus estimates. So really, what's the difference between direct measurements that we prefer and what we'll talk about today, and the other bulk type measurements of mass flux that are prevalent in the industry. And after we do that, we'll talk about flux tracers. We'll give you an introduction into this tool that we've developed and a method that we use at Regenesis to quantify contaminant mass flux and groundwater mass flux or groundwater flux in an aquifer. And then we'll take some questions and answer at the end. So what is mass flux? At a very fundamental level, flux is proportional to flow, or you can think of flux as flow. And so it doesn't matter what it is. When you're talking about flux, you're really wanting to know what the quantity of something is that's moving through some unit area that you define. So we have here that mass flux or flux can be the amount of something that's passing through this unit area as a function of time. And so you can use flux to quantify light, or you can use flux to quantify traffic, the flow of cars. For our purposes, we're going to follow groundwater flux, and that's going to be Darcy flux, or the flow and flux of contaminant molecules. So that's contaminant mass flux. So really, flux is just anything that's moving through some area versus time. That's what we're measuring here and talking about. And so what does mass flux mean for us on the remedial scale? And so we're going to define flux as the rate of flow through some plane of compliance, which we'll see here. So if we look at our site that we have here, we've got our groundwater plume here as our groundwater is moving through our area of our source zone where we've got contamination. And what we start to see is that we've got this picture where you've got varying amounts of contaminants that have been contaminant mass that's moving along with this flowing groundwater. And since you've got different heterogeneity, you've got heterogeneity in your aquifer, and what that means is that this heterogeneous flow of groundwater is moving more and less contaminants through these different zones that are present in our aquifer. And so if we have this picture here where we've got varying amounts of contaminant concentrations kind of layered on top of the fact that you've got different groundwater velocities. If you just take individual well samples, you're not really going to see this nice picture that we've got here in this transect of varying mass flux, but instead you just get averages over your groundwater concentrations in your wells. And that really gives you an incomplete picture. But what we want to be able to quantify and measure on a remedial scale is where are those zones of most mass that's migrating through our aquifer, because that's what our remedial options, that's what our remedial strategies are going to address, is that actual mass and not so much the concentration that's present in the aquifer. And so, what we have here is this complex picture of mass that's distributed unevenly, and that's really what we need to understand in order to do proper groundwater remediation in situ. And so we'll quickly take a look at the units that we're going to talk about in this presentation, because they're not the same concentration that we're used to. It isn't just milligrams per liter, but when we're talking about groundwater velocity, we're talking about our units of in centimeters per day. So how much water is moving through this transect that we care about in these different regions as a function of time. And then mass flux, we're going to talk about it in terms of milligrams per meter squared per day. And a lot of us aren't used to using these units, so I'll quickly point you to kind of a quick conversion to get our minds thinking about these units that we're going to be mentioning today. And so you can see here on this table, we've got our Darcy velocities listed from 2 to 20, and we're going to convert that to a seepage using a porosity, which is, you just kind of have to layer that on to go from a Darcy velocity to a seepage. But really what I want you to take away is that at 2 centimeters per day, you're talking about 100 feet per year. And then at 20 centimeters per day, you're talking about closer to 1,000 feet per year. And then for mass flux, that's we have to make an assumption about our groundwater concentration is. So we're going to say 5 milligrams per liter. And then if we use those same groundwater speeds, either Darcy or seepage, you can see that at 100 feet per year, you would have a mass flux of 100 milligrams per meter squared per day, going up to, if you had 1,000 feet per year, you'd have 1,000 milligrams per meter squared per day at a groundwater concentration of 5 milligrams per liter. And so we kind of color code it so that we can follow how much this mass flux is, or what the Darcy speed is, just kind of in simple, is this fast or is this slow, or is this a lot of mass flux or is it little terms. And so this understanding of mass flux we've really adopted this here at Regenesis, but we're building on, I'd say, 20 plus years of understanding about mass flux and the power that it can bring to remedial design, and really just site conceptual models and understanding what we're actively trying to manage on contaminated sites. And so we aren't the first ones to talk about mass flux or push for its use in a remedial sense. We're really building on the foundation of others here. There's numerous studies that have been funded and reports that are available both by ESTCP funded projects, and the ITRC has got some excellent guidelines that are out there. And out of this body of work, there's a whole host of tools available to you, both in terms of software, and then also EnviroFlux. I'm showing a picture here of a passive flux meter, which is a tool that you can use that's available from EnviroFlux to measure mass flux and groundwater flow in wells. And a recent publication I'd like to point out that really kind of drives home some of the importance of mass flux strategies and kind of where we are in the industry. It was published in Groundwater Monitoring and Remediation, most recent article, or most recent journal by John Horst and authors. They do a really good job of talking about mass flux in terms of what it can be used for from not just a remediation standpoint, but also from a regulatory standpoint, because mass flux and this idea of quantifying not just concentrations, point concentrations, but really understanding how much mass is migrating off of a site, this really gives you better ideas of what's the risk of a site, and the mass discharge, following mass discharge really helps you better understand the actual amounts of contamination that are leaving your site and going off site into receptors. And so for further information, I'd recommend you check out this article. And with that, I will hand things over to Craig, who's going to get more into the practitioner side of mass flux.
All right, thank you, Paul. So in my part of this presentation, I want to talk to you about measuring mass flux and why it's important to do so. On the right, you see a fairly large plume, probably a half-mile long, and it's commonly accepted in the industry to use permeable reactive barriers to manage these long, elongated plumes. It's cost-effective, it's highly effective, remedially speaking, and when they're designed right. So it's a commonly used approach, and you typically orient them perpendicular to flow and the long axis of the plume. And you can see I've oriented my barriers in the turquoise lines. So there's about eight PRBs there. PRBs, however, are highly sensitive to contaminant mass flux, both in the short and the long-term performance. And in the short-term performance, if you miss a mass flux zone that matters, you're gonna get holes punched in your PRB. In the longer term, if you don't have the mass flux dialed in reasonably well, you're probably gonna have a shorter operational life than you think. In short, I just wanna give you the sense that if you ignore the collection of mass flux data, it puts your project in peril. So why is measuring mass flux important? Most flux occurs in a small fraction of the aquifer. And this just simply allows us to have a more targeted approach. So it's commonly accepted that 90% of the mass flows through 10%. You can see at 80 at 20. You'll also see some authors saying 70-30. Pick whichever ratio you think is best. But the point being, you need to find those zones that matter the most. As Paul mentioned before, mass flux can be used as a better performance metric. If you have a baseline, an in-remediation period, and a post-remediation period, you can document how much mass has been removed from the system in a flux basis. It closely aligns with risk and risk management. Mass flux results closely align with critical PRB design elements. It's a measure of the dynamics of the mass that moves. The compliance plane that Paul talked about earlier directly correlates to a PRB's face. It's a very powerful concept. How much mass is the PRB seeing every day? And the time element, a little more subtle, but a very important element, is that it allows us to make better predictions and do better remediation for operational life. We can estimate an operational life much more effectively if we have a time element. Mass flux measurements, function well in varying levels of heterogeneity that are present. And folks, heterogeneity is present at all sites. I don't care how clean you think your sand is, you have subtle differences in hydraulic conductivity that change the velocities, and so the mass flux. For remediation, heterogeneity is where we need to measure. It's where the action is, folks. So it helps us identify and quantify the zones where contaminants move. It does not have these embedded assumptions that we will talk about shortly that are present in water supply traditional method measurements. By that, I mean bulk averages, et cetera. We'll talk about that shortly. The results are remediation centric, so they're at the scale and usable data that you can directly plug into your remediation design. It also quantifies and measures zones that control the size and the shape of the plume. I cannot stress enough about that quantification measure of zones that matter, the ones that control the size and shape of the plume. So as I mentioned previously, when we use water supply methods, in this case, I'm in the figure to the right, I'm showing an extraction well. You can see the various levels of contribution during the pumping cycle contributed by various levels or units within the target treatment zone, that being the saturated screened interval. Bulk aquifer measurements like this do not help you determine where mass is and how fast mass is moving. So if we think about estimating mass flux using traditional methods, that's what I'm going to call it, it's an indirect measure. So if we view contaminant mass flux as a wall with underpinning bricks, the contaminant mass flux is made up of a hydraulic conductivity number, which you've gained either through an extraction test or a slug test. And the results are presented as a bulk average. Again, recall the figure I just showed you. Groundwater concentration is also an average. You can think about the sampling of your well as the view of the concentrations that all these various units have contributed. Effective porosity, if you're using, like the rest of us are using seepage velocity as your velocity measure, you are using an educated guess. That's another variable of error that's possibly introduced into your system. And finally, you have the least variable, the least error prone, which is a gradient. It's a reasonably good direct measure. So 3 out of the 4 components that go into a traditional methods of estimating contaminant mass flux have varying levels of error introduced. Whereas if you compare that to a direct measure using an in situ flux tool, it's a direct measure of mass flux. The results come to you in milligrams per square meter per day. That's a very PRB centric, remediation centric result that you can use. It removes those 3 out of the 4 contaminant mass flux potential error sources. And the results are used directly, finally, an important point for us, and it makes mass flux so important here at Regenesis, is that we use these directly in our flux-based design models. We plug the data straight in. So as Paul mentioned, okay, Craig, you've told me all the errors and prones and the benefits, but what are the methods? What are some modern methods to measure mass flux? Well, I'm going to focus on direct measuring tools today, but as Paul mentioned earlier, there are 2 really outstanding documents that I refer you to. CERTIP ESTCP 2006, Mass Flux and Mass Discharge by Newell et al. This is in support of his roadshow, probably between 2006 2009, where he was talking about mass flux, mass discharge. It's a really nice piece of work. The ITRC 2010 is a follow-on to this in use and measurement of mass flux and mass discharge. This document covers the waterfront on various ways of measuring mass flux, the benefits, the weaknesses, the strength of all the different methods are addressed in this document. So I would highly recommend you review these. So today, our focus is on direct measurement tools. These are tools that are designed specifically for mass flux measurements. You have 3 sources for these tools now. Domestically, you have EnviroFlux with their passive flux meter. Internationally, you have the iFlux meter. These folks are out of Belgium. And finally, you have our newest offering, Regenesis, which is our Flux Tracer. Paul will be mentioning this and talking about this shortly. So in this slide, I wanted to talk about how mass flux varies significantly over very short intervals. So if you look at the left-hand column, that's depth below casing in feet. So it spans approximately 9 feet, between 6.75 and 15.75 feet BGS. There are Darcy velocities associated with each, which range from less than 2 up to a 12. So there's probably just around a multiplier of 3 if you take the measurable 4.3 into 12. So there's your 2 to 3 times. There was no PCE present, but you can see TCE and DCE are presented in milligrams per square meter per day. And you can see the variability across the 10-foot well screen. Now, when we're talking about this, you see that in this case, most of the mass is moving through the highest Darcy velocity present. And there's a couple of hitches here where you have a 9.2, at around 11 feet, and 6.8, where you get quite a bit of mass, but the real mass is down at the bottom. But this quickly puts the perspective in what should I be emphasizing and what should I be not worrying about so much. In the next slide, I'd like to show you the opposite of that, if you will, where it is not directly tied to groundwater velocity. In this well, if you'll look at the right, just right of the MW1, you'll see the depth below top of casing is 111 to 121 feet. So we have a 10-foot vertical section. Our Darcy velocity varies between 6.9 and 14.9. That's roughly between 300 and 716 feet. Well, there's your 2x velocity variability again. But if you'll notice that the high mass flux zone is really up in the kind of not the highest, but near the highest. And I think it's really important that there's no rule that says hydraulic conductivity and velocity are always going to be your high mass flux zones. If you made that assumption, you would probably be missing that zone between 111 and 113 feet, or you might not be applying as much material as you should be. Finally, I'd like to cast your eye on 111 with 556 feet of groundwater velocity and 120.1 with 583 feet. Those numbers are roughly the same. However, look at the difference in the mass flux, 2.5, 53. Again, I'm trying to make the point that there is no rhyme or rule. There's no rule of thumb that's going to help you understand this unless you directly measure it. So in this next slide, I'd like to discuss how we do as a group comparing flux tool to bulk aquifer measures. So what this is a weighted average of the flux tool versus the bulk aquifer measurement. So the weighted flux tool divided by the bulk aquifer measurements in terms of velocity. So there are 25 sites, and when the tool reads lower than the bulk aquifer, you get a fraction. When it reads greater than or higher than the bulk aquifer reading, you get a whole number. So what you have is a 25 site evaluation. And on this, you can see we're right roughly 3 times. And the tool reads lower than the bulk aquifer result, which is really good because you're probably going to save some money and have a really good, strong design. On the other hand, if you're on the right-hand side of the green, the three successfully estimated velocities, you're going to be in trouble really quick because you're going up from anywhere from 1.4 to 32 times. And if we just think about that in gross numbers, so we're right 3 out of 25 times, that's 12%. But we're wrong in the wrong direction, which is being underestimating it using traditional methods 68% of the time. So we just aren't very good at estimating the real velocities that matter most in terms of using traditional methods. And in my final slide, I just wanted to offer this one up just to help calibrate what flux, high, medium, low. This is just a distribution for 21 sites. What we did is we took the maximum flux reading for each of the sites, and they kind of distributed out this way. 35% or less than 20 milligrams per square meter per day. Now, at 20 milligrams or less milligrams per square meter per day, that is a really straightforward design that is all day long successful. When you get into less than 150, 63% of sites were less than 150. That you start to have, I need to tighten down a lot of engineering pieces. You know, what areas are really moving the most? Where should I be emphasizing that? How robust is that 150 milligrams across the barrier face? Where do I need to put reagents? Where do I need to put sorbents and destructive elements? Things like that. Finally, 100% were less than 1,100, but I'm going to update that to 4,000. We just had a recent update where the highest mass flux we've seen to date is around 4,000 milligrams per square meter per day. And the final bit of calibration piece is 4,000 milligrams per square meter per day is a roughly 50 milligrams per liter moving at 500 feet a year. So that's, neither of those two variables are outside of most of our remedial experience. So beware, these things are out there and they're out there to be measured, and you need to measure them before you design. And with that, I'll pass the ball back to Paul.
All right, thanks, Craig. So now that Craig's kind of painted this picture of the different methods that are available to measure mass flux and quantify mass flux, and kind of highlighted the importance to us of using direct measurements, we'll kind of first take a step through how these devices work. How do passive methods of measuring mass flux and groundwater flux work? And so all of them kind of share some common elements. So the devices, whether you're using EnviroFlux's devices or iFlux or Regenesis Flux Tracers that we'll talk about, they all have the same principles, and that's that they're filled with some type of sorbent media, whether that's granular activated carbon or ion exchange resin. It depends on the contaminant that you're trying to capture and measure. And so, you know, that's one part that they all have the same. And so this media that is filled in these devices, it's impregnated with a leachable tracer. And this tracer is there to, and it's going to displace at a rate that's proportional to the groundwater that's moving through the zone that this device is put into. And the one difference, or the one device that is in development, I know iFlux is working on a digital groundwater flow meter that doesn't use tracers, but aside from that, most of the devices, they use this tracer-based method that we're going to talk about here. And so the device is then put into a target well for typically 2 weeks. That's the length of time that we like. And you know, you're going to drop this device, and so you can see here in the image on the right, this is an example of one of our flux tracers that's been deployed. And it sits in the well for 2 weeks, and so we've got the opportunity now for our contaminants that are moving through our zones of the aquifer to start accumulating on the device, while simultaneously our tracers are being displaced that we'll then later use to measure how much groundwater flow was passing through those zones. And so each of these two measurements, both the mass flux and the groundwater flux, or Darcy velocity, they're measured at the same time, but they're independent measurements. So what I mean by that is the measure of mass flux that we're getting is we're measuring that and quantifying that based on how much contaminant mass shows up on this sorbent material that's in our devices. And the groundwater flux is done by the tracers, but even though they're happening simultaneously, they're completely independent measurements. So the mass that shows up doesn't inform on the groundwater flux, and vice versa. The tracers that are being leached doesn't tell us or is not used in any of the calculations for the mass flux that we make. And so again, our target is to try to delineate these more permeable zones from the less permeable zones, which may or may not carry more or less of our contaminant mass flux. And that's what we're trying to quantify with the use of these passive methods. So this image comes out of one of the papers that we really like from Mike Annabelle and his group at University of Florida, which Mike and his lab, they really did a lot of the groundwork in developing this as a method. And so I just wanted to point out that this image came from their paper, and we really, they've done a lot of great work that we're really just building off of here. And so again, the principle is that as groundwater is moving through, we're capturing contaminant mass in each of our vertical zones. And as that's happening, that's what we're going to use to figure out what our contaminant mass flux is. So what's the contaminant mass that arrived in this tracer, or sorry, in this sorbent material that we've put in? And at the same time, we've got these groundwater tracers, or these soluble alcohols is what they are. They're leaving at some rate that we kind of understand, and that's what we're going to use to figure out what our groundwater flux is. And so that's, you can see what's going on here in the cross section of our device. You know, this is happening at each of the intervals of our device that's been put in the ground. And what we're trying to gather is this graphic or this data that we can plot out by placement in our well. Because again, we're trying to figure out where our vertical zones are in our aquifer that we need to pay most attention to and target with our remedial efforts. And so what you'll see is you get this Darcy velocity and this contaminant mass flux kind of plotted out as a function of depth. And you can see here that, you know, if this is the data that you got back off of a site, this is going to help inform which of those zones that are more permeable might be carrying the most contaminant mass versus your more slow-moving areas that have less mass and less groundwater fluxing through them. And as Craig mentioned before, it's not always that your highest groundwater speed or groundwater velocity is carrying the most mass flux. And in this example, you would expect that if you were just following your groundwater speed, you'd be missing the fact that most of your contaminant mass is in the zone that's above, that's got a more modest but still high groundwater velocity. So this is an animation of what the Flux Tracer is. So this is the device that we've developed here at Regenesis that, again, really builds on what others have developed and had out on the market for longer. And just kind of walk through the elements of our device. So the whole device is supported by a well cap that can take the entire weight of the device and hangs it into the well. And because the depth that you're going to deploy this device to, it's different for every site. So we will cut a custom cable that will be pre-packaged and sent along with the device and stored on this transport stool. And then depending on the length of the interval that we're trying to measure, there's going to be 5 or more or less of these units, these modular units or canisters constructed and pre-assembled in the device that you get. And then there's spacers in each of these canisters, which we'll see some images of in just a moment, that are there to provide or to prevent upward flow or really vertical flow between the units of granular carbon when it's installed. And so this is an image of what the Flux Tracer looks like for shipping. And so again, our emphasis on development was trying to make this as user-friendly of a process as possible. And so when it arrives pre-packaged, it's folded up like this, and it's tent poles together, and it's quite easy to manage. And so really our whole concept was around designing this device to be something that's easy to use, and that's what we strive for in the development. And the devices they're installed by the user. So what we'll do is we'll collect some basic information that we need from you about the well, the depth, the type of contaminants that you're interested in, and the well construction materials. And then very importantly, the depth that we're deploying this device to. So all of this information is gathered up front. So what that allows us to do is send a device that doesn't require any assembly once it gets to the field. So the device is, it's really ready to go. So what you'll see when you get the device is it'll look like this, but packaged up. So each of our canisters are just individually wrapped. All you'll have to do is take the packaging off, and this device will be ready to insert into the well. Installation takes really no more than about 10 minutes. And then after the device has been deployed for like we mentioned before, 2 weeks, it'll be ready to take it back out. And on the withdrawal side, you will return the device intact. So as it goes out to the field, it will be repackaged basically to look the same as the way that it came out. And you'll put these sleeves on it, put it back in a bag, and you'll return the device to Regenesis without doing any field sampling. That's a big one. This saves you the hassle of having to sample anything in the field in this device, but instead the whole thing comes back intact, where we'll disassemble it, take the sorbent out, make the measurements that we need to in our lab, and then when we're finished with that, we will generate the report of the data after we've had the opportunity to work up the samples in our lab. And so to give you a couple more images here, or a better picture of what the devices look like when they're shipped out, they go out in a cooler, and it comes with, I kind of skipped over this, a little sample kit that has just some things that are nice to have in the field. So there's a tarp that can help you prepare out the area that you're going to be working, some simple tools to help you open up the device and really just manage the whole process a little bit easier once you're out in the field. Installation, as we said, is really just as simple as sliding these canisters down into your well. And you can see here, just a 2-person team is really all you need to install the devices into your well. And then, withdrawal is basically just the reverse of this. You'll take the device back out, lay it out on the tarp that's provided, package it up, fold it back up, and stick it in the cooler. It's really quite a simple process to deploy and retrieve. One of the most, really the only thing you have to do after installing the device is make sure that you've put this little retaining clip in place. And the reason I point this out is just to highlight the simplicity. This little clip is really just there to make sure the devices don't come apart from one another as it's sliding down the well, but instead all 5 of them, if that's how many you're putting in, they stay close together and in that zone that you expected them to be in. And really that's it. It's as simple as that. A little bit more about the construction of the devices. So they're all stainless steel. So the entire device that goes into the well is stainless steel. It's filled, like we said, with a granular activated carbon that's got these leachable tracers that are preloaded onto them to measure the groundwater flow. And when it comes back to the lab, we fully decontaminate these between sites. So we reuse these devices. And to support that, we have a laboratory grade washing machine that's able to really clean these things as the same as laboratory glassware, so that there's no cross-contamination between sites. They get fully decontaminated after they're used in one site before they're prepared for another. We seal them, and they're, we say, tamper resistant. And really that's not because we're worried about someone messing with them, but what it does is it allows us a little bit more control over the data process. So we know that what goes out and what comes back, we have a clear understanding of where the devices were. So if you don't have to do this, any field sampling, it just takes the error possibility out of sending back samples that had to be labeled and taken out in the field. And it's just a lot more simple to the user. So the construction of the canisters took a little bit of work, and what we've settled in on is this self-centering design that makes the devices so they kind of snake down the well easily, and there's low risk of them getting stuck up or hung up, even if there's a little bit of a deviation in the well. This junction that they have between the canisters allows them to kind of move like train cars, we call it. And so in all of our field deployments so far, they've gone quite smoothly, and we expect that to be the case in the future. Since I'm in R&D, I'd like to point out some of the development work that we did along with the devices. And so you got a picture here of a box aquifer that we had to build, kind of a test cell that we used to validate the flux measurements that we were making. And so the image on the left, you can see we had set up to do a dye test, just kind of a tracer test to make sure that this test cell that we built had even flow across the whole region that we, across the entire screen interval that we had. So that's a little 2-inch PVC well screen you can see stuck down in some well-packed material that we built here in the lab at Regenesis. And then on the right, you can see one of these individual canisters being installed so that we can run our just our test measurement where we were calibrating our our Darcy speed or Darcy flux measurements with our box aquifer here. And so the report, so after we get these devices sent out and deployed and they come back, this is what we're after. We want the design team here at Regenesis, this is the data that they use to plug into our passive barrier designs. And so this is really what we're after when we deploy these tools, of course. And so just wanted to step you through the three main elements that the reports have within them. And so first is just the data table. So table one is, this is the numbers that we've been talking about through this whole presentation. So we've got our Darcy velocities that are reported at 1 foot intervals. So all of the devices that we send out, we generate reports and data at a 1 foot resolution. So we could go, you could just take fewer measurements, but really what we're after when we deploy these devices is the resolution that we need to design and be successful at the remedial scale. And for us, we've kind of found that 1 foot, it's not perfect, but it's definitely good enough for the remedial scale. So all of the devices that we send out, we really require that we do measurements at that 1 foot resolution. So you'll get your data reported as your Darcy velocity. You see here we've got 3 different contaminants listed on this report. So PCE, TC, and cis-DCE. These are the contaminants that we're currently able to quantify and report on in our lab. And so that's what you'll get. You'll get this data back for these different contaminants, again, in this milligrams per meter squared per day. And I've dropped in this table that we looked at the beginning of the presentation, along with the color coding to highlight a point that we're trying to make when we're generating these reports. And that's that the numbers are for us and the design team so that they can install or put in the correct doses of our remedial products, whether it's Plume Stop or S-Micro ZVI. But what we're also trying to do is just calibrate everyone in terms of what these numbers mean. And so we've got this color coding to try to orient the recipient to, what's a easy to manage lower end flux versus what's a high end flux that, as Craig mentioned, you really got to pay attention to when you receive numbers like this. That's the type, these 1,000+ milligrams per meter squared per day. This is the mass flux level where your designs just become that much more tenuous if not done properly. And the second table, table 2, that's we report flux derived concentration. So what that means is that if you could take instantaneous water samples in the well that you've installed this device, this is the groundwater concentration that you would get. And these aren't concentrations that we measure, but instead these are concentrations that you would generate from if you had a Darcy velocity and a contaminant mass flux reported from the data that we have. And then you can use those 2 values to then figure out what the groundwater concentration would have to be in order to match up with that Darcy speed, Darcy velocity, and the contaminant mass flux. And these oftentimes are matched up quite nicely with what you might expect in your well, which you would be measuring in that monitoring well, but they're not always the same or close. And that gets it, and the reason for that is what Craig was speaking about before, is that you're just not sure if your well is being biased by an individual zone, more or less. And so this is just kind of a depiction of what that groundwater would look like if you could take just snapshot concentrations at discrete depths. And so we'll kind of end with some final thoughts before we turn it over for questions and answers. We hope that we've been able to paint this picture of that mass flux and flux-based thinking. You can really use it to improve your designs and preparing to do a remedial, to take remedial action, but really it also just helps conceptualize what's really going on these sites better than just groundwater concentrations from wells alone. And that direct flux measurements, we feel like they aid the in situ remediation planning better than these bulk average methods that are more often used at the moment. And finally, we've walked through what Regenesis has developed with these flux tracers, which are now available for our CVOC sites that we work on. And really, I wanted to stress that mass flux has become such an important design element for us that we really are required to do this type of analysis on any of our Plume Stop sites that we work on now. And so with that, I will finish our presentation and we'd be happy to take any questions.
All right, thank you very much, Paul. That concludes the formal section of our presentation. So at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a couple of quick reminders. First, you will receive a brief survey following the webinar. We really appreciate your feedback, so please do take a minute to let us know how we did. Also, you will receive an email with the recording of this webinar as soon as it is available. All right, so let's circle back to the questions here. This one is a question for Craig. And Craig, the question is, the use of flux tools are restricted to wells. How do you extrapolate away from the borehole/well?
Well, I have a couple of methods that I like to use. One, as part of the DVT that Paul mentioned that we developed here at Regenesis, is we spent some time understanding the details of the target treatment zone by doing continuous core detailed mapping / logging. And so you're able to track individual units across the site, at least within your target treatment zone. A second method, and it is really a powerful method, is to use well-tied MIP HPT methods. That is, you have a flux tracer study performed in a well, and then you perform HPT MIP to inform on the various units that you can readily see and identify using the flux tools, and track them and map them across the target treatment zone across the site. So those would be the two ways I would go about it.
All right, thank you very much, Craig. So here's another question. This one is for Paul. Paul, the question is, will flux tracers be available for use on any site or only as part of a Regenesis project?
So at the moment, we are using flux tracers exclusively on Regenesis design sites. So when you work with our design team, our sales team, we are recommending that we put them on all plume stop sites, and for the moment, we will keep them in-house. You know, we'll see where things go in the development of it if we decide to offer them kind of to the wider market. But at the moment, we will be, these are really just for use as a part of a Regenesis project.
All right, thanks, Paul. So we do have another question here. This one is for Craig. And Craig, the question is, how do I know that the flux tool doesn't serve as a groundwater conduit or restriction?
Oh, good question. Well, the hydraulic conductivity of most flux tools on the market is usually quite a bit more than the surrounding aquifer material. So as an obstruction, I don't see that you're going to have water moving around a flux tool. It'd probably preferentially move into a flux tool. I do think that the other element that is kind of embedded in that question is, well, what if it's upflow? You know, if it doesn't restrict flow and therefore move it around the tool, what about it? How do you keep it from moving up through the unit? And we do that in a variety of ways. Our tools are segmented into 2-foot units, which are independent. Within that unit, we have a washer. Likewise, I would say that in use of the EnviroFlux tool, they also make use of washers to prevent or gaskets to prevent upflow through the media.
All right, thank you very much, Craig. So we have another question here, and this one is for Paul. And Paul, the question is, do you only consider mass flux when coming up with your treatment or groundwater speed as well?
Sure, I'll answer this, and then if Craig has anything else to add to it, I'll let him chime in. Mass flux is really, that's what the barrier and your remedial agents are most interested in. And so what I mean by that is when you think about, you know, what are you putting your, whether it's absorptive media, you know, in terms of a plume stop barrier or ZVI, those reagents that we put into the ground, they're intercepting the mass flux. So really that is what our eye is most tuned into, is the mass flux. That's what the numbers in the design phase are targeted to. And groundwater velocity, you know, we also care about that. And the reason is because along with groundwater velocity, you get more. You could perhaps have faster influxing of things like dissolved oxygen. So if you're doing an ERD design, you have to account for an increased demand on your reagents. In the case of ZVI, from something like that, and groundwater speed also just is a complicating factor. You're more aware that this zone is faster moving. There might be more movement of your reagents post application. So in terms of the actual numbers, when we're doing dosing, mass flux is what we care the most about, and groundwater speed is just a very important element to have your eye on for just the overall picture of site design.
I'd like to add to that comment and build on Paul is that the velocity is an important component, but mass flux is exactly what we need to design PRBs. The flux, pardon me, the velocity is really about how much residence time will be in your PRB, as well as, you know, as Paul mentioned, the flux of competing electron acceptors if you're doing an ERD barrier, for instance. So both of those elements are important, but I place mass flux above velocity. So I'm in agreement with Paul there.
All right, thank you very much, Craig and Paul. That is going to be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. If you'd like to learn more about remediation solutions from Regenesis, please visit regenesis.com. Thanks again very much to Dr. Paul Erickson and Craig Sandifer, and thanks to everyone who could join us. Have a great day.